Thank you. Cool. So this will be a fun talk. Memory leaks are a big problem. Here we go. Is this on? Oh, boo. That's okay. I have the technology. So as you mentioned, I'm Ben, co-founder, CTO at Lucid Software. Been there forever, basically my entire professional career. It's been fun. We make Lucidchart. Lucidchart is one of the biggest JavaScript applications on the web. Actually, it's TypeScript now in the course of the last several months in an effort to get better tooling. We migrated en masse 500,000 lines of JavaScript to TypeScript. If you ever want to hear about that project, that's a fun one too. I'm sure that'll turn into a conference talk at some time. But there's not a lot of projects of this size, but it's enormously complex, and we are seemingly constantly in a battle against memory leaks. In fact, we have an entire team of developers with whom I'm actually sitting right now, dedicated to tracking down performance problems of all kinds, including memory leaks, and tracking them and making sure that we understand what our performance is out in the wild on people's machines, and then trying to improve it. This is a quick snapshot that I took this morning from one of our performance dashboards where we actually measure memory usage, JavaScript heap size usage in the wild. So each data point here is 1 day's average memory usage in a browser tab. It has been getting better. So my team has in fact been, doing useful things. I show this to everybody who questions that. But this we've seen like a 15–20% drop in average memory usage. Each one of those comes from 3 or 4 million data points from people's browsers out in the wild each day. And so it's really gratifying to see our ability to turn that down. So before we get started on the tools themselves, I want to do a quick review of garbage collection, how it works, very quickly. Prepare yourself for some serious oversimplification. What we have is what are known as GC roots, the garbage collector roots. These are the places from which you can reference all objects in your JavaScript heap. And those objects are typically, the root would be like window or something that owns window, actually. And then those have references out to all these other objects. Objects have references to each other. And the job of the garbage collector is to navigate that whole map, figure out who has a path, a retaining path, it's called, back to the root, and keep those, retain them, and then sweep away everything that has no path to it, regardless of if they have connections among themselves. So this thing is fully automatic, happens mostly in the background. So, well, modern JavaScript virtual machines will have a generational garbage collector that sometimes runs in a separate thread and sometimes blocks your UI thread. But regardless, it's a process that you mostly don't have to think about, right? You use things, you throw them away, they get garbage collected, all of my memory problems are over, right? Wrong. It turns out that memory leaks are really, really easy to cause in any environment, including JavaScript. How can you leak memory that doesn't get automatically reclaimed? Well, you could add an event listener to some DOM element from your class, and then you think you've thrown away all the references to that class, but the event handler is still in the list of event handlers on the DOM element, and guess what? That thing is part of your object, and your object lives on. You could set an object as data on a DOM element using something like jQuery. You could have like this global cache saying, I'm going to remember these calculated values and forget to clear that out. And so even though there's a big piece of data that you're not using and haven't used in a really long time, it can remain in memory basically indefinitely. Even things as innocent as a console log. In the Chrome tools, when you do a console log, it will log out a sort of navigable object, so you can like expand it and look at its references and see what's downstream and so forth. And that navigable thing continues to work even if you throw away all other references to the object. So guess what? You console log something out. It is stuck in memory forever until the user opens the dev tools and clears the log, which is really unlikely to happen. There's any number of ways that you can wind up with objects. And so the question then becomes, okay, how do I analyze a situation? How do I know how much memory I'm using, where it's been allocated from, why it hasn't been garbage collected, and sort of how it looks over time? Am I constantly allocating new memory, or am I just allocating a ton of memory up front, way too much, and that's the source of my problem? And there's a variety of tools in the Chrome dev tools to help you with that, and we're going to walk through a quick example of each of these. There's heap snapshots, allocation profiles, and allocation timelines. Heap snapshots are really the go-to. These are the workhorse of the memory analysis tools in Chrome. This will tell you what objects are there right now. So it takes a snapshot. Every JavaScript object that has not been garbage collected, what does it look like? Where was it, or not where was it allocated, but what function was its constructor, if any? How do they reference each other? How much memory do each of them retain? But you can also compare these snapshots and say, do I have new objects now that I didn't have before, or what things were constructed or destructed or garbage collected since the last time I took a heap snapshot, and also which things failed to be garbage collected. So that's really honestly the go-to tool for most of this. There's also allocation profiles, which will tell you what code paths are allocating the most heap memory. So what code is making a bunch of garbage? Even if it's being collected, garbage is not free, right? Garbage costs CPU time to generate, put it into the heap, and then to be collected out of the heap at the end. So the allocation profiles will help with that. We'll show that. Allocation timelines are for objects that aren't yet garbage collected. Where were they allocated in the code? And is my garbage being rapidly collected? Like, it'll actually show you over time, here's the memory that's being allocated, the amount of memory allocated during each 1 second interval or something, or actually a fraction of a second interval, how much was allocated and how much of that has so far been collected. So you'll see this sort of stream of blue, and it'll slowly peter down to gray and empty out as the garbage is collected from older times. So now is the fun part. It is demo time. So I mostly agreed to do this talk because it gave me an opportunity to write an asteroids game on company time. I needed an example application with an amount of code that would be sort of understandable and that we could look at and analyze together. And so I made this. Yeah. And now everybody knows that the best strategy, is to stay still, because otherwise it is really hard to reason about. But you can also move in here. Here we go. Yes. Okay, so what we have here is a pretty simple game being played on a canvas, and I'm going to give you a quick walkthrough of the code in here. Well, this mic is questionable. Okay. What you have is you have this thing, the button. This is just a menu that's a button, starts the game, it constructs a new game object. Game object, in turn, constructs a player, adds a canvas element to the DOM, listens to things like the mouse move and mouse down and mouse up events, starts with some random asteroids, and then starts this, when you say start, it starts this animation frame loop. And then when we stop the game because you've been hit, we end the animation frame loop and go back to the menu. And the game, of course, we just create it and start it, and so when we chuck you back to the menu, the game should be gone and garbage collected. So first thing that I'd like to do is show you the place that I start is not actually in the memory tools. I'll click on this performance tab, and this is actually a new thing as of the last couple versions of Chrome. And this does a sort of holistic view of all the things that are taking up time and memory in your application, and it will record it over time. So if we say, all right, we'll start recording this, we run the game. Oh man, I suck at this. Okay, here we go. All right, so we stop, and it'll go. So what we have here is a profile of the JavaScript execution, which is pretty fast because this is not a complex game, and I have a pretty fast computer. And this down here is the memory heap size over time during the course of the games that I just played. it is going in the wrong direction. It is going straight up. It's normal for this graph to go up because you generate garbage in a lot of ways, even very innocuous ways like returning ad hoc structures from functions. You'd see it go up and sort of come down when you'd see this drop off as a garbage collector cycle ran, and it would go up and it would drop off again. But this is just a steady rise. And so the first thing that I would do is I would go and I would take a heap snapshot to see what is there right now in memory, because apparently there's a whole bunch of stuff in memory. If we come over here to the memory place, we have the 3 different things that I mentioned. We go to the heap snapshot and click take snapshot. And what we will see here, I should note that I artificially inflated the size of these objects by putting 100,000 random integers on them so that they would show up, because otherwise everything is just noise. It's so small. So we have here all of the objects that are currently in the JavaScript heap. You can sort them in a number of different ways. The retained size is basically the way to find the big stuff. Okay, this is not just the size of the object itself, but the size of itself plus everything that it retains a reference to that might cause those things to not get garbage collected. And so we find near the top here, we actually have 5 game objects still in memory, despite the fact that there's no game running. And as far as I know, nobody has a reference to the game. And so the question then is, where are these things? Now, if you expand this, you can actually see the individual instances, right, of this game object. Oh, excuse me, there's not 5, there's 4 of them. This one is the distance. That's from the garbage collector route. How many references is it before it reaches these objects? There are 4 objects in here. If you click each one of those, you can actually see its contents. So you'd say, oh, well, it's holding onto this array of asteroids and this canvas, which is red because it's not in the DOM anymore, but it actually still has a reference to it, so that thing's not getting garbage collected. But where is this object actually? If we look down at the bottom, it shows the retainers. So here we say, all right, for this game, it looks like from the window, some sort of array, something, there's this code in this function that's holding on to it. And actually, if you hover over this, you get a little hint that'll take you back to the code where this function is defined. And it'll actually show you this function is holding on to a reference to the game. See, at this point, I remember I used to be hooking mouse events on the canvas element, but I changed it to the window because I wanted the mouse moves to continue to work when you are off of the screen. Anyway, so I changed the event listeners from the local element to the window, and we never unhooked those. And so this event listener is still here, and it references this, and this is the game, right? So this thing didn't get garbage collected. So we're going to fix this really fast. We're going to say, this is really fun to try to do this with a Band-Aid on my thumb while I'm trying to run the touchpad. This is extra, super awesome. Also, this is a really fun thing for demos. I would never actually use this on my production systems, but you can actually set up the dev tools to let you edit the files directly on your file system. And then you just save and refresh. So we take those ones, we copy them down to our stop function, and we change these to be remove event listeners, and we'll refresh and we'll try this again. Okay, we refresh the page. We start the game, we play, we lose, and then we go to the memory and we take another snapshot. Let's clear this out. And the game is still there. Again, we look at this. There is another one. Oh, yeah, I said another event for the window resize, right? So this is the way that it works. You can look at the retaining paths and you track them down, and one by one you wind up squashing them, right? You say, do I? Oh, thank you. I'm good at this, guys. All right. Yeah, okay, there we go. Like I said, this is how you convince me to come give a talk. At this point, no game left, right? We've successfully killed it. All right, yeah, okay. All right, one down. So, so that's the heap snapshots, right? There's also other things that you can do where you can say, for example, if I start another game, and then we take another snapshot, if you compare this one to the previous one, oh, come on. No? You're gonna refuse? Oh, curse of the demo here. No, you don't. So you click, you can't select them both. All right. I'm gonna try this real quick. Just take one, take another. You can say, wow, I take it back. That drop-down has an item in it called comparison. And it will actually show you the ones that are, yeah. No, it's not. So, and actually none of them are working. This is sort of amazing. Let me kill this. Yeah. I'm going to try this again. And take one, and take another, and hey, there it is. Good, you get to kill them. Okay, but oops. Right, the idea is that you can take a snapshot, and you can get into a state where you believe that the memory usage should be very similar, and then you can take another snapshot and compare them. So there I was at the menu. Here, I've played a game. I'm back to the menu. I can take another snapshot, and I can say comparison. And this one will compare to snapshot 2. And it will say, all right, what's changed since then? And it will show you the delta, like how many more or fewer of this kind of object are there than there was during that other snapshot. And so that's a good way of saying, for example, when we're in Lucidchart, you go from one page to the other page, back to the first page, back to the second page, back to the first page, and we'll do a snapshot before and after and say, well, having gone somewhere else in your document and coming back, we should have discarded all of the stuff that we generated in order to render the other page by the time that we've come back. And that's going to be a very effective way of saying, you know, this should be about the same as the previous snapshot, and find those leaks. Okay. All right, so that's snapshots. The next thing is allocation profiles and allocation timelines. I'm going to show the timeline first, because it makes sense in the context of this application. So if I start this allocation timeline, and I start the game, and I start shooting things, you see the blue up there? Those are objects that are that have been generated. There we go, and we'll just stop it. Okay. The blue objects have been generated. Actually, the entire height of those little bars is the amount of memory that's been allocated. The blue portion is the part that has not yet been garbage collected, okay? And what you can actually do is you can select a portion of this, like this, and say, all right, what got generated here that has not yet been garbage collected? It can't show you the objects that have been garbage collected because they have been garbage collected, but it can show you the things that are there that are still there. And so, you know, if we do this again, we start the game. Oh, man. Okay. Right? I'm so good at this, guys. Here we go. Oh, man. I need to dodge. Okay. And we stop. Okay. What I see is a whole bunch of blue in here, right? Now, my earlier games got all garbage collected, right? Those all got cleaned up. Fantastic. But what's left over here, remember, I stopped it while the game was still running. So this should be able to tell me, while the game is going, what stuff is still there? Like what's getting allocated that I'm not cleaning up? And if we look at this like a little chunk here, and you'll see like, oh, there's some new asteroids that got created, and there's a handful of bullets that got created during this time period, right? And those objects were generated then and still haven't been garbage collected. And just like the heap snapshot, you can actually come into this and look at each individual one and say, where is this? Actually, this appears to be like bullet number 10 in the currently running game, right? This gets to be more exciting when you leak a lot more memory, but we just cleaned up a big memory leak. However, if we look at the performance here over time, now we should be able to see that hopefully we have the healthy pattern. Yeah. Yes. Okay. Okay, there we go. Oh, man. But we still have this steady upward climb. So if you look at the blue bar here, the blue line graph, you can see that a garbage collector ran right here. I'm not sure if I can make this. Hey, all right, let me stretch out a little bit. You can see a garbage collector run happened right here, right? And there's small garbage collector runs, because as I mentioned, modern JavaScript VMs run a generational garbage collector. So things that have been allocated recently get cleaned up frequently and inexpensively, and things that last a long time get put into an earlier generation, and then those get checked less frequently. And so we had a full garbage collector run probably that happened right here. And we have a whole bunch of little bits of up and downs, but we are steadily rising on the amount of memory usage that we have. And so this is still sort of a mystery here. But if we look back here, the reality is we wound up with this long list of bullets that got generated. There's never more than like 8 of them on the screen at a time. But you can actually look into the contents of these things. Oh yeah, there's my 100,000 pieces of junk data. You can look at these objects here. Oh, except that the game has now been garbage collected and I can't actually access them. These things, you can using this, this is a difficult case because things are happening rapidly, but here you can actually navigate to the object itself in the console. You could do here, window, what is that, 26, whatever, down to like bullets, 18, and figure out where it is or why it's still there. It turns out in this case, we're not clearing them off when they go off the screen, right? They reach the edge of the screen and they just keep going off into infinity, which again is a pretty simple fix, but one that if you're not looking at a variety of different tools, you might not realize. If you just use the heap snapshots and you said, here's what it looks like before a game, here's what it looks like after a game, and it looks good, and you look at the timeline and you see the thing going like this and jittery, you might be able to see it. But you really need to use a variety of these tools in order to track down all the issues that you might have. You come back to the source, and I think that we can actually clean these guys up. We can probably just make the move function return something and just kill these guys. Don't judge me, I'm writing code fast. Okay, and probably say like if well, that also could have been one statement. All right, I think that'll work. Resolving host. Come on, it's localhost, you suck. Maybe this won't work as well. It might be. No, I think it's good. Yes, it turns out. This is the reason why things like FastJS work. Sorry for the aside while I wait for the internet to start working. The FastJS is a thing that is a much faster implementation of built-in JavaScript things like for eaches on arrays, because they don't have to worry about things like users splicing stuff out. They explicitly don't make the guarantees that are made by the built-ins. Things like supporting sparse arrays and splicing things out of the array in the middle of the for each and so forth. Okay. I'm not entirely sure if this refreshed, but the spinny thing stopped going. So at this point, we should be able to come here, clear out our data, rerun this, and try to survive as long as I possibly can. Okay, close enough. At which point we see this. This is what a healthy memory graph looks like. So you see there's some amount of allocations happening as time goes on. Because I made my bullets very, very heavy. You get actual noticeable jumps for each individual one every 100 milliseconds. But you have it going up and down, and you have the garbage collector runs happening on regular intervals. It's not taking up a ton of time doing the garbage collection. So at this point, we've made our application healthy. Now, we've only covered 2 of the 3 big tools that are available to us in the memory tab. The other is the allocation profile. And what this will do is tell you where in the application the allocations are happening, right? Where is the actual piece of code that is causing this thing to be allocated? And so here, if we start this one, we say, all right, here we go. Oh man, okay, there we go. Okay, stop. Okay, so what you have is you have, just like you would have with a CPU profile, where there's like how much time was spent in each method, and you can do it in different ways, like bottoms up, like which methods had the most time spent in them directly versus which methods had the most time spent in them or the things that they called. You can do the same thing here with memory allocation, where you can say, all right, which things generated the most memory themselves and which things with their children. In this case, because I just allocated a whole bunch of junk memory, you can say, all right, who generated the most, if we sort it by total size, the tick function, the frame running function. Turns out that does everything. But if you look at the tree here, you can say, all right, what's inside the tick function? Well, we do a for each, and we run for each on the bullets, and we break the asteroid. No, we're generating asteroids. This is and you have over here a link to the function itself. And you say, here's right directly in this function is the place that we're allocating the big chunks of memory. Now, this is a very boring example because it's very small. I actually have a really large Lucidchart diagram that I wanted to run this on for you. This is a fun one. This one has something along the order of 6,000 or 8,000 objects on it, and once in a while we get people sending us examples saying, here's something that runs really slow. Maybe you could make it run faster. We went through a couple of iterations on the memory tools with this particular document, trying to get it down from its outrageous amount of memory allocation during load. Because what we found was when we ran the CPU profiler while loading up this big application with this big document, most of the time was spent in the garbage collector, actually. It was something like 80% of the time spent loading this document was spent running the garbage collector over and over. And what happened was we got close to the amount of heap memory we were allowed to have, and so we were thrashing through the garbage collector, where there's very little available space, but it had to navigate essentially everything. It had to do a full generational search through all of the objects, and as your number of objects that you have reaches up into gigabytes, then it turns into a real problem. But this one is a lot more fun here. If we start the heap profiler, we refresh again, I'm going to give us a 60% chance that this works, since the internet on my machine here has been a little sketchy. I would love it if this worked. There we go. This is a fun one. As I mentioned, I sit on the team with the people who are full-time working on improving the performance of our application. And the things that are the most gratifying to work on are where there are really big, really obvious performance problems, and you can tell if you've made them better. You know, we've gone through a lot of processes over the course of the last year of instrumenting performance in production. We actually use Zone.js, which is this open source library that monkey patches every entrance point to JavaScript. So anytime that you have a event that fires, or a timeout that fires, or an animation frame that fires, or a WebSocket that gets new data, or any way that you could possibly start executing JavaScript, it actually passes through. So you have the ability to look at every JavaScript execution that happens. And we actually started measuring how much time do we spend in JavaScript out in production. You know, on average for everyone. We did the same thing with memory, where we said, you know, for certain browsers, as long as the user hasn't turned it off and it's usually rounded to the nearest megabyte, you can actually get the heap size of the JavaScript heap very quickly. And we started reporting that data back as well, which is what led into a lot of the things that we're going to see here. But I think that we might be out of luck here. Resolving host. I don't think you can see it there because it's clipped off. Oh well. Regardless, it's the allocation profile was the tool that actually resulted in us making this document that previously would crash out the browser after spending like 20 minutes trying to load into, oh, there we go, into a document that, presuming your internet works, you know, loads up in something like 30 or 45 seconds because it was generating so much garbage. And it was interesting because it really was garbage. It was not memory that we were using. It was not objects that were long-lived. We were generating data based on the partially loaded document, and then we were generating it again when it was a little bit more loaded, and then we were generating it again when it was a little bit more loaded. And what happened was we generated something on the order of, don't judge me, like 3 gigabytes or 3.5 gigabytes of data during the course of loading this document, when in fact, when it was done, the whole JavaScript heap size was a couple of 100 megabytes. And so something was clearly off. And that's a really difficult thing to debug, because you can't look at it at the end and say, what do I have and how do I not generate it? Because that's not the problem. The problem wasn't the stuff that I had. The problem was all of the stuff that I built and then threw away. And so what this allowed us to do was to look deep into our code and find, there we go, and find the places where we were actually generating way, way too much data. And so here we have a much more interesting set of information where you say, all right, we're legitimately generating, what's at the top? About a gigabyte worth of data while this document is loading. It used to be several times that. But then you get to look at this and say, all right, what are the heavy things? Right? There's this anonymous function that itself internally is generating 150 megabytes of data during the course of loading this document. Like, let's go look there and see what's in the code. There's also a chart view here, which is fascinating. This is not, the x-axis here is not time. You can get this sort of flame chart out of a CPU profiler, and it will show you, like, over time, who's eating up the CPU, like, what is the stack trace at this point in time where we took the snapshot on the CPU. What we have here is a stack trace, and the x-axis is the amount of memory that was allocated. Like, when we reached 100 megabytes allocated, what was the current stack trace? When we reached 101 megabytes allocated, what was the stack trace? And so what you get is it's scaled by the amount of memory that it generated, not by the amount of time it took. And so you're able to look at the big fat bars here and say, oh, something is going wrong here, right? Remeasure if new fonts, like we're remeasuring some text, right? And we're generating 321 megabytes of data while remeasuring all the text on this document, which may or may not be reasonable depending on how many tens of thousands of words are on the document. But it gives you a target, right? It gives you the big fat target to go look at and say, this is the next place that I'm going to investigate. Okay, I think that's basically all that I had for today. Thank you everybody for your patience. I think we're gonna take questions though. So we have another 10 or so minutes. So if there's any questions, I'm not sure if the plan is to pass around a mic, but I'm happy to take any questions about this or basically anything else. We got one in the back. Yep. Oh, the JavaScript profiler? So that's actually the old JavaScript profiler. So the performance tab that I showed here is actually the official replacement for the JavaScript profiler. However, it does not have all the features of the JavaScript profiler. And as right now, basically my full-time job is profiling the application, I will take the one that still has all the features. The features that are missing in the new one are things like focusing in on a particular function, so that if you take a large CPU profile and there's one function that you care about, for example, I'm trying to improve rendering performance, I will do a bunch of actions on the document while I'm profiling it, I'll stop, and then I will focus on the render method and the things that it does, so that becomes 100%. So when it shows the percentage, it'll say 100% in the render function, and here's all the different pieces. Because I don't particularly care about the amount of time that got spent responding to the XHR requests and so forth. But that feature is not yet in the performance tab. And so I'm not sure if the plan is to leave the JavaScript profiler available indefinitely or only until they reach feature parity or what. But you can find it under the Hamburglar menu over here. Under more tools, there's JavaScript profiler, and it will actually make the tab appear. Yeah. Question was, is Chrome the only browser I use for this stuff? In practice, it is almost the only browser that I use for this stuff. Periodically, we'll have performance issues in other browsers. Fortunately, Chrome's dev tools have pushed other browsers to produce decent dev tools. Before Chrome, the best dev tools were actually in Internet Explorer, which is ironic because they are awful. The browser, that is. The dev tools were actually basically okay way before the browser was. But now there's reasonably good tools everywhere. Safari actually is the only major browser that has a instrumenting profiler instead of a sampling profiler. So what we have here and in most places is every so often, and I think it's every 100 milliseconds, they will take a stack trace, right? Like what's the current stack trace, and they use that to generate the data that you see. In Safari, what happens is they actually recompile all of the functions that you have in JavaScript, and they measure the amount of time that is spent executing them. Now, this is a problem because it changes the performance characteristics of your application. But what it gives you is the ability to measure the number of times that a function is called, where there's no way of doing that with a sampling profiler. And so if there's some place where I worry that the problem might be that this function is just being called too often, or that's the thing that I'm trying to improve, I will actually open up Safari on a Mac and use the profiler there. So yeah, there are tools. There's different tools available, but by far Chrome has the best set of performance profiling stuff, including memory profiling stuff. Yeah.
What data do you log about production users and their performance stuff, and then how do you turn that into actually fixing things?
I'm sorry, the last part again?
Oh, how do you actually turn it into fixing things? How do you
Oh, yeah. So, yeah, that's a whole conference talk on its own. I was going to do it, except that yes, oh, sorry. Question was, what things do we measure in production? What things do we measure in production, and how do we turn that into actually fixing things? With memory, it's difficult because the only thing that you get is the current JavaScript heap size, and you only get it for Chrome. And it's rounded to the nearest megabyte. And it's may or may not have had garbage collected. However, more than 50% of our users are on Chrome. And so it's a big enough data set that for us, it's sufficient to be able to look at things and see real trends among our users. And we actually collect it once per minute. So once per minute, we actually ping home with the last minute's summary of performance data. It's just things like how much time was spent running JavaScript and tags on different JavaScript executions, and in memory, just one snapshot of saying, here's the amount of memory right now, if we've got that data. And so since we send it back once a minute, we can actually look at trends over time per editor session. So in the case of memory usage, the first time that we put it in, we had zero visibility into this before, but I ran a linear regression on 500,000 editor sessions against the time passage versus the memory usage. And we were, the heap size was growing on an average of 1 megabyte per minute, averaged across all of our users. And so if you were there for an hour, it might have crept up from 200 megs to 250 megs worth of memory usage. And that was like the average across all of our users. So some of them were much worse and some of them were basically okay. But that actually was an interesting insight that we didn't foresee. In terms of the JavaScript execution, we can get a lot more data. And so, so what we do is we keep track of when JavaScript executes. Like I mentioned with Zone.js, we can know when it starts and when it ends. We also are able to keep track of microtasks, so the things that happen as a result of promises. And we say all of those execute synchronously. And we know for certain that if JavaScript is executing synchronously for a long amount of time, users are not able to interact, right? Like it's totally frozen on the UI thread. And so what we did is we said, for one synchronous set of JavaScript execution, where it's the task and all of its associated microtasks, we measure how long that took. And then we bucket those, and we say, how many times during the course of the last minute was JavaScript holding the UI thread for 16 milliseconds or longer, 50 milliseconds or longer, 100 milliseconds or longer, quarter second, full second or longer. And how much total time was spent frozen up for that threshold. So we'd say, how many 100 millisecond pauses, which are like just enough for the user to be like, okay, like it feels goofy. How many times did that happen in an average minute? And how much time did the user spent locked up for that amount of time during that minute? And so we send that up every minute for every editor session. And then we essentially dump that into a Redshift database where we do a whole bunch of statistical analysis on it. But we also tag them. So if it's each JavaScript execution, during the execution, we can fire tags saying like, oh, this was rendering. Like during this JavaScript execution, we rendered a frame. Or during this JavaScript execution, we like sent this XHR, requested this URL, or responded to a JavaScript or an XHR from this URL. And so those tags then get aggregated up. And we can look at it from one day to the next, or the next week, or the next month, and say, all right, which of these have moved? Has rendering got better or worse? Has generating the data for a document save started causing people to drop frames more than it has in the past, right? And so we're actually able to look at this in some amount of detail, and it's easy for us to add these kind of tags. So we have this massive database now. We are constantly running out of space on our Redshift cluster, actually mostly from this data. But I smile because we've gotten fantastic data out of this. Just in the last week, there had been a performance regression that had been going for 5 or 6 weeks, and we hadn't been able to figure out what it was. But we knew from the amount of tagging that we had done that it was from a set interval. There was a set interval that was running, and it had suddenly caused like the number of times that people froze up for 100 milliseconds or more to go up by like 30%, 40%, something ridiculous. But it was an untagged one. We tagged a bunch of them, but not this one. And so we went through and tagged all of them in our code, every single one. And we released this update, and we started watching the data, and it was still untagged. And then we realized it was coming from a third-party library, like a third-party thing that we had put on the page, which we hadn't updated, but they had updated. And what they were doing was now causing like 20% of our total user pain in terms of performance. And we were able to know that for certainty because of the level of detail of the data that we were collecting. So anyway, I cannot recommend highly enough instrumenting in the wild to the degree that is, that is possible or reasonable what your user's performance looks like, because you find stuff like this that like we never would have known, right? And our users were suffering. So anyway, that's the long answer. Yeah?
Are there other tools that you use?
In terms of just generally helping with performance. Let's see. It's mostly the Chrome DevTools, frankly. Like 95% of my job when I'm figuring out performance issues, it's in the Chrome DevTools. As far as actually reproducing, seeing the issue and fixing the issue, it's the Chrome DevTools. As far as internal tools to know what thing to fix, it's basically what I described, and that's my whole tool set. Yeah. Good question. So the question is, say you have a button with an event handler on it, and then you, like, somebody put an on-click on the button, and then we throw away the button. Does the button still exist? That depends on what happened to the person who set the event handler. Okay, so if the object that constructed it, that gave it the handler, the function that the on-click actually calls, if that function refers to objects that are still retained, or yeah, then the button will remain there. Whereas if it's been thrown away, it'll be thrown away. So sorry, it's very difficult to explain in the abstract. In the context of my game, there was the canvas, right? The canvas element. It got thrown out of the DOM when the game was over. It had a context menu handler on it, right? When you right-click it, we like do a prevent default to keep it from doing the standard context menu. That one I did not have to unlisten to get my game to garbage collect and to get the canvas to garbage collect. And the reason is that the game itself had a reference to the canvas, and that the event handler had a reference to the game, right? The event handler was doing something to the game. So they referenced each other, but there was nothing outside that was still being retained back to the window that was referencing either of those. And so although they were connected to each other and interrelated pretty heavily, as soon as we removed it from the DOM and threw away our references to the game, it was all cleaned up. Yeah. That's a difficult question. I know that there are coding styles that are intended to help make sure that that memory is dealt with appropriately. In fact, there's whole languages built around the idea that if you code carefully, you can do like, static compiler-based, like Go doesn't have a garbage collector, but you also don't do memory management because the memory management is actually guaranteed by the compiler because they can analyze your code in that depth. So like there are ways of doing it. In practice, especially in JavaScript, I have yet to see someone do this successfully, frankly. Like in terms of like, is there a way of writing code that's gonna make it much less likely? The biggest things to remember are you've probably screwed up event handlers. That's the reality of it. Like if you're leaking out memory, in my experience, like more than 50% of the times that that's happened to me, it's because I've leaked out event handlers. And not just DOM event handlers. Like you have objects that fire events, right? Like you can have things that have callbacks where you're like telling this object, please notify me whenever this event happens, and those internal relationships, you don't realize sort of how far that web goes, and you wind up retaining a whole big chunk of your application that you didn't use before. And so we use the closure library, and they have sort of this set of classes for event handlers and disposable things and so forth that help to be more explicit in your code about saying, I'm done with this thing. In fact, we recently made it so that if you use one of the disposable objects and you call dispose on it, we actually replace all of its entries with getters that throw an exception. So if you ever try to use something that has been disposed in any way, it will actually blow up at runtime in dev. And like that, trying to be more deliberate about saying like, let's clean up after ourselves and let's make sure that we're rigorous about that has been helpful. Yeah. Oh, so, okay. So, the question then was, when you're looking at the output here, there's a whole bunch of like anonymous function, anonymous function, anonymous function, anonymous function, right? The Chrome tools are pretty smart about classes. If you use, and not just classes, but also, prototype kinds of classes. Like the Chrome dev tools are pretty smart about it. You can name your functions. So if you have anonymous functions, you just do function space the name and then whatever for like anonymous inline functions, and that will give them a name so that it will show up in the whole set of DevTools. We actually start from TypeScript, and so our code has already been transpiled by the time it makes it to the browser, even in dev. But the TypeScript transpiler is pretty good about maintaining names and actually giving things names automatically to make sure that things like the DevTools work well. But by and large, putting names on your functions is the biggest thing. But it's actually not as big of a problem as you think, because almost everywhere in the DevTools where you see anonymous function, you can click through and see which function it's talking about. So it's generally not a big problem. Yeah? Oh gosh. I turn off source maps. They're turned off in my browser right now. So source maps, for those who are unaware, if you start with another language like TypeScript, you transpile to JavaScript, it produces either a separate file or a really big encoded comment at the bottom of the file saying, in this output JavaScript, like which pieces of this line up to the original source code, so that you can get things like stack traces from your original TypeScript files rather than from JavaScript. And so the reality is it's not worth the pain, in my experience. Actually, on the whole, source maps have not gotten good enough for me to like using them. It causes, we have a lot of code. And so you load up the DevTools, you open the DevTools, and the first time you go to the source files, it will lock for us for like 20 seconds or longer while it figures out the source maps. And then it never works as well as you want to. You put a breakpoint, it's like you're seeing your TypeScript and you put a breakpoint, and it may or may not stop exactly where you wanted it to stop. And it caused enough pain ongoing. I turn them off. I think most people on my team do. Yeah. We do. So we use the closure compiler. So we use TypeScript we use the TypeScript compiler to go from TypeScript to JavaScript. We actually use a project called Sickle that was built by Google as part of a way to sort of a bridge to the closure compiler. And then we've actually written probably 20% of it too, because we're probably the only big client of it outside of Google. But then the closure compiler is by a far cry the best minimizer that exists in the market for JavaScript, but it does require a lot of work to work with. But we have so that's sort of our pipeline. We start with TypeScript, we go through either the Angular compiler and Sickle, and wind up with the closure compiler for our final blobs.
Awesome, thanks very much.
Yeah.
Round of applause for Ben, please.
Yeah.